the topic of my presentation is just to give you a scientific perspective of what does forecasting model validation means and calibration, what is the difference, why it is so important to evaluate the difference between these two. And this work has been made with Tom Jordan, that is from University of Southern California. Okay, at the beginning, when I was an undergraduate, I pretended to become a scientist. And trying to understand exactly what science means, I discovered that was much less easier than expected. In that years, there was a paper published on Nature that reported a statement by Sir Peter Medawar, that was a Nobel Prize, ask a scientist what he conceived this scientific method to be, and she will adopt an expression that is like at once solemn and shifty-eyed. Solemn because she feels she ought to declare an opinion. Shifty-eyed because she is wondering how to conceive the fact that she has no opinion to declare. Actually, asking to my senior colleagues, what is the scientific method, what is science, I received completely different ideas about what science is. And that was a little bit surprising to me. In the same papers, in the papers that have been published in that years, there were severe critiques to science based on the fact that we were not able to exactly to explain what science means for us. I don't know, Feyerabend is a provoking character, was very clever guy, but he likes to provoke. But his critiques were based on the fact that we were not able to explain why science was so different from other human enterprises. Even more dangerous from the scientific point of view was the Thomas Kuhn statement in one of the very famous books, The Structure of Scientific Revolution, in which said the science is not about truth or reality, it's about transient vogues. That was the opinion of many leading person at that time. And this is probably somebody that you know is the mathematician that he said, physics is not different from literature. And the basic point is that objective science is just a matter of consensus. There is no truth to discover. Again, believe me, for scientists, this is a very big punch in the face because, yeah, we pretend to say something truth about the nature, about how the world works. And this is also more pervasive. This is a recent paper published on Nature about the string theory. The string theory, I don't know who knows that, but according to the people working on string theory, if a theory is sufficiently elegant and explanatory, it does not need to be tested experimentally. That's something really, again, that's very strong statement, but this is it. This is what about the string theory says. So now the reaction of scientists, what I like most is some sort of statement released by the IIIAS that gave a lot of emphasis to the fact that what makes the difference between science and other human enterprise is the predictive capability. Science has a predictive capability. Literature and all the other human enterprises that are very important as well, but they do not have a predictive capability. In particular, in this statement, there is a couple of words that are critical for our business, that is accurate predictions. Means that you need to make forecasts or predictions, and then you have to decide if it is accurate or not. And that's exactly what has been the reaction of the scientists. Actually, this is not a novelty, and I like a lot to quote also Richard Feynman, that was one of the most prominent physicists, and that was used to say science is not useful if it tells something about an experiment that has been already made. It's important only when you can say something that is not yet happened. And this is exactly what we would like to do with the forecast. That for us, this is a way to emphasize again and again the importance of forecasting as a scientific enterprise. What is the problem of model validation? And with validation, I'm saying something a little bit more than calibration. I'm going to talk a little bit more about this difference. Model validation simply means that you have a model, you have a set of independent data, and you want to be able to say if your model is good enough or not, or can be rejected or not. The problem is that, in particular in the natural system, we live in an open system. The closed system is much more controlled. Everything can be controlled. So when you look at past experiment or future experiment, everything seems to work pretty the same because you can control everything. The boundary condition, initial condition, whatever. The open system is completely different. And the basic point here is that when you look at, in an open system, when you look at the past or the future, you see two completely different words. And this is also one of the biggest motivation for one of the most common cognitive bias that we have in natural science, that the hindsight bias. That means everything is clear after the fact. After the fact, you see tons of publication in which you can explain exactly what happened. Nobody tells one word before things happen. And this is just to tell you what is the very strong asymmetry that we have in an open system. Predictive science look at forward, try to learn something from the past, of course, but it's not just a matter of describing what has been observed, trying to get some common feature that can be applied for the future. And again, this very strong asymmetry between backward and forward also raised a lot of concern about the possibility to validate open systems. Here I just reported that there is a very famous statement by Niels Bohr: prediction is very difficult, especially when it is about the future. This is just to tell you why there is a huge difference when you look at the past and you look at the future. And this is a paper that has been published in 1993 on Science, Verification, Validation, and Confirmation by Oreskes et al. That's something that I strongly suggest you to read, because at the very end they say, okay, there is no way to validate a model in an open system because everything can change. So basically, model validation is just simply a heuristic. You can't say anything of truth. Of course, we have a different opinion, and we try to explain how we can eventually validate a model. But this is just to tell you that the problem exists. And this is something that the last slide just to introduce the problem. The validation problem in an open system is that all models are wrong. Everybody knows that. And some people ask, okay, but if all models are wrong, why we should validate them? We already know the answer. It's just a matter of how many data I have to reject a model. It's not a big scientific issue. And here I just reported one statement by Andrew Gellman that is probably the most objective Bayesians that say, well, for us testing one model with the data makes sense, but not for validation. It's just to understand where my model didn't fit well the data. And for this reason, he tested the posterior distribution instead of the prior, the data not to be independent necessarily. They just want to understand how they can fit the model at best. So, okay, now let's move to how we try to solve this problem. Everything is based on some sort of hierarchy of uncertainty. And for introducing this, I'm talking about earthquakes. I'm talking about the seismic hazard that actually is the forecast of the ground shaking in one specific site, in one specific time window. So that's, again, it can be easily generalized to the wind, the velocity of the wind, amount of rain, to everything you want. We just simply introduce this because this is where all discussion have been made. A hierarchy of uncertainty, why this is important? Oh, here I just reported some papers that you can read. The first one is introduce the problem, why we spend some time to do this. Okay, uncertainties are different and pervasive. That's very important for us in the sense that when you read the literature, you can find a lot of completely different definition of uncertainty. The basic point here is that uncertainties are different. We know that. We don't have only one kind of uncertainty. We have different kinds of uncertainty. Is it important or not to keep them separated, to classify them? The answer in the framework, unified framework that we provide is yes, that's important, and we have to keep them separated. And another important point here is that if the final goal is the probability assessment to describe a behavior natural process, uncertainty has to describe the uncertainty on the process, not on the model. That's another important thing, because if you change the model, of course, you change the uncertainty. But the process that you want to describe, it has uncertainty, and you want to describe this kind of uncertainty. Well, a classical view, this is Alain Cornell that made a significant contribution at the beginning, the 68, to describe different kind of uncertainty in seismic hazard. We describe the aleatory variability like some sort of inherent randomness of the system, of the process. It is objective and irreducible, because this is something related to some intrinsic randomness of the process. Epistemic uncertainty is about lack of knowledge, and then the more I study about the process, the more I can reduce that. And this was an important issue because it has been discussed in important document that have been released in the United States in the 90s. So let me tell you briefly what is a seismic hazard, just to give you some idea. I think that this is very similar to what you have in different fields. Okay, this is a distribution, a statistical distribution is a survival function for one specific random variable, that here is the ground shaking, horizontal ground shaking one specific site. But again, it could be everything. It could be the height of tsunami wave, the ashfall loading for volcanic eruption, the wind, whatever. And we are used to describe this distribution through a survival function that is the probability of exceedance of some value of intensity. And this is in the two hierarchical model, this is the aleatory variability. This is some sort of intrinsic randomness. Okay, now, for instance, here we reported the 2% in 50 and 10% in 50 that are important thresholds that are used by engineers to build the building code for earthquakes, for the building resisting to earthquakes, and so on. Now, what is the epistemic uncertainty here? The epistemic uncertainty is, okay, how can I build this distribution? If I ask two different modelers, they can come out with quite wide range of distributions. And that means that I don't have any idea that what is the true distribution that I have to use. And this is what we call epistemic uncertainty. It's a bunch of curves, it's a bunch of distributions. And so in this way, we can say, okay, this is the epistemic uncertainty because it's something that I don't know. And I can eventually try to reduce. So, but is it easy to make this distinction? I would say, well, no. Because as long as I learn more about the process, maybe something that I thought it was irreducible, maybe it can be reduced. In the pure deterministic view, coming from Laplace, everything is deterministic. Everything. So at the end, the more I study about the process, the more I can remove any kind of uncertainty, arriving to a deterministic equation. So in this way, I can say everything is epistemic. Because at the end, it's just a matter of studying. I can reduce that. And then also there are description of aleatory variability as based on model-based or physics-based. Here, I just reported a couple of statements that has been given in important document, for instance, the NRC review of the Schack report. Schack report is an important document in the United States that set the basis for the seismic hazard and for how the seismic hazard has to be built for the building code. The value of an epistemic aleatory separation to the ultimate user of PSHA is doubtful, because nobody knows exactly what is epistemic, what is aleatory. Some people can say, oh, this looks aleatory, but if I study more, this is not aleatory. It can be reduced as well. As you can see, is very doubtful. And this is physics-based. This is a report by James that, again, it's very strong character, but he said, I don't see any physical probability, basically. It was a pure Bayesian, but when you toss a coin, well, if I know perfectly everything about how the coin is balanced, what is the force that I give for the flipping a coin, maybe I can do much more than 0.5. I can do much better than 0.5. So I don't see any physical probability related to that. So everything related to the fact that what we mean with probability, for instance, in James, it is clear that say is a degree of belief, is nothing physical, it's just a degree of belief. So, and on the other hand, people say, no, the probability is a frequency. You can say frequency of what? But these two kinds of definitions are very important for model validation. How can you test a model if the probability is the degree of belief, is subjective degree of belief that can't be measured, basically? So again, this kind of tension is really important for us. It's really important for scientists that pretend to say something about the truth. In this slide, for instance, I reported a couple of views about frequentists and subjectivists look at the problem. At the very end, for subjectivists, everything is epistemic. It is very difficult to hear a Bayesian talk about aleatory variability and intrinsic variability. And for the frequentist, at the end, they just estimate one number, that is a frequency. Where is the epistemic uncertainty? There is no way to report in the pure probabilistic framework the epistemic uncertainty. And again, this kind of ambiguity brought a lot of very important and strong critiques to science about what is the nature of what we are doing. Are we doing science, or are we trying to find a consensus about something? That's really important, because if you try to find a consensus, other people say, oh, I have a different consensus. So it's quite important for us, because everything here, seismology, volcanology, has a very thin layer between the science and the social usefulness of our information. So it's important to communicate properly. So, and this kind of distinction can be explained a little bit better just looking at the mean. For instance, one thing that we do is we have a bunch of curves, and at the end we calculate the mean. For every single point on the y-axis, we calculate the weighted average of all the probability, and we got some sort of mean hazard. You know that you can calculate the mean, or you can calculate any kind of different ensemble modeling. But at the very end here, you are collapsing all the curves into one. Okay, for the pure frequentist this is the mean hazard is the best estimation is the frequency, for instance, of exceedance of the value x naught. The problem is that all the dispersion of the curves has been completely thrown away. You don't have any kind of memory of the fact that these curves tend to be close to the mean or very far from the mean. Here, in the Bayesian subjective framework, this kind of stuff is the Bayesian model averaging. It's very similar to the Bayesian model averaging, in which the dispersion of the curves do not make any sense. I just have to say I work in what we call MECE, in mutually exclusive and completely exhaustive set of curves. That means one of the curves must be the truth. And I just simply calculate the average, take into account that the weight is the probability of that curve to be the true one. And for the Bayesians that do not pretend to say something true, they say, okay, this is a classical way in which I can calculate the Bayesian model averaging. that is the way in which, given the information that I have, this is what I can do. Perfectly fine. In this case, however, the probability is not a frequency, it's a degree of belief. So when you have the mean hazard, I can say, well, from one side, the ensemble modeling 100% won't be the truth. It's something that, again, depending on how many data I have, I can always reject it. So what is the meaning of calibration? I think that in the paper written by Tillman, everything is so clear. Given the set of information, this is the best that we can do using this framework. That's perfectly fine. We would like to say something more. We would like to say something about the truth of the model. And for instance, here, again, what we are used to do, and also in seismology, we are used to make some sort of testing only about one model. That could be the single model, could be the average model, could be any kind of ensemble modeling. But at the very end, one can ask to itself, why I'm doing this? If all models are wrong, what is the advantage in doing this? I can say, okay, this my model explains well this data, but maybe I can't say anything for the future because everything can change. And again, for science, this creates a problem. This really creates a problem. Pragmatically, why we should keep separated them? For instance, keeping the bunch of curves. Let me show this example that is taken from the MAP seismic model of United States 2008. It's not the most recent one. Here you have Memphis and you have San Andreas Fault. And this is the distribution that I told you before, the probability of exceedance curves. And if you look at the solid line represent the average. And if you look at the 2% in 50, that is a very important value for the building code, the two curves intersect. It means that the mean hazard for the 2% in 50 is the same value. And people say, wow, I don't believe that. You can say that Memphis and San Andreas Fault have the same kind of probability or to overcome this kind of acceleration. If you look at the dispersion of the curve around the mean hazard, you have a completely different picture. In Memphis, since the models are much more uncertain, we have much less data, you see that the dispersion of the red curves around the mean are much wider. That means that the true probability of exceedance could be 1 order of magnitude less. So again, what I'm saying is that giving this kind of leaving this kind of information could be very important for the decision maker. Another plot, still in California for Redding and Los Angeles. You have a bunch of models that try to estimate the probability of exceedance. These are the bunch of curves that have been cut for one specific value. And here the distribution, what you get. 2% in 50 is still the average for both sides. But here the model tend to agree almost around the same value. Here, it seems that all the models tend to have a bimodal distribution. So again, this is important because it gives you an information more about how the models, what the model tell you about your estimation. Again, this distribution has been built cutting the bunch of curves for one specific value of the ground shaking that has 2% in 50 to be overcome. And as you can see, the bunch of curves tell you two completely different things. That to me is important, also for the decision maker, is important to understand exactly this distribution and how it works. So now we add an additional level of uncertainty. Probably you know this guy that was in the Bush administration, Donald Rumsfeld. There are known knowns. The first time that I heard this, I say, okay, he is joking. Probably what he's saying is very profound for us. Because in the first case, there are known knowns, there is some sort of aleatory variability. Known unknowns, this is what we call epistemic uncertainty. This is an uncertainty that we know that exists. Now, there is an additional level of uncertainty that is unknown unknowns, that by definition can't be put inside the model because they are unknown. And this is what we call ontological error. So, in essence, we move to a 3-level of uncertainty hierarchy in which we have aleatory variability, that inherent randomness of the process, epistemic uncertainty, and also an ontological error. And we will see how we can define that. Basically, the most important point to introduce this kind of 3-level uncertainty hierarchy is through the definition of an experimental concept. Why this is so important? Because at the beginning, you have to define what is the probability of what, and then you estimate this frequency with some sort of uncertainty, and so on. I will show you an example, probably is the best way to go. At the very end, the ontological null hypothesis is something like that. I have a bunch of curves. My ontological hypothesis is, okay, the true process that exists has to be inside this bunch of curves. This is just to tell you a very long story short. And that means the true distribution belongs to some sort of family of curves that are inside the bunch of curves that I showed you before. And this is very different from testing the mean hazard, because I can tell you that the mean hazard will never be the true model. So the mean hazard, sooner or later, will be rejected. From here on, I'm talking about the experimental concept. The experimental concept is the only thing that we need to define, to establish this sort of 3-level hierarchy. That's very important. I will do some example just to tell you what does it mean in our framework. So, the definition of experimental concept is just a definition of a sequence that is exchangeable. You know very well what exchangeable means, but very important. For instance, I can define a sequence per year in which I have 0 or 1, 1 if I got some sort of event, a 0 when I don't. If I can define this sequence exchangeable, that means that for the definitive theorem, that the frequency must exist, independently if each single event comes from a different distribution, but a frequency of this exchangeable sequence must exist. Okay, that frequency is what we call aleatory variability. So the aleatory variability is not anymore related to the true process that could be enormously complicated. It's only related to the data generating process. A process that generates this sequence that is exchangeable, and then the frequency of these numbers for us is the aleatory variability, is the intrinsic randomness. So everything is related to the fact that we can define this sequence exchangeable. And again, that's very important because this also makes a difference between physics and social science or whatever. In social science, when humans are involved, it's much more difficult to establish an exchangeable sequence because humans in the same condition should learn from the past. Should. Not always do, but they should. So it is very difficult to think about an exchangeability in time. Physics, the physical laws remain the same. So every time that you decide to have a sequence, yearly sequence of, for instance, of magnitude 9 or nothing, you can have an exchangeable sequence. Definitive theorem declares the existence of a frequency, and that frequency for us is the aleatory variability. That is related to the data generating process. Here, just an example about what the experimental concept is a selection. Again, I'm interested in the frequency of the squares. I know that if they are exchangeable, there must be a frequency of the square. The square could come from different distribution that we never know, okay, but with that frequency, we can establish some sort of long-term frequency of the square inside the experimental concept. And the exchangeability is also for the past and the future. That's very important. Okay, so let me talk about the example that we had before. Bunch of curves, we cut the curves for one specific value, then the ontological null hypothesis for us is like to say the true experimental concept that the true frequency, for instance, to overcome this value x0 has to be inside this range. So if I observe that, case A and case B, that's important. If I consider the mean hazard, both will be rejected. If I consider the whole distribution, the case A won't be rejected, case B will be. So this is just to tell you what is the difference, heuristically, what is the difference between considering only the mean hazard, that is the red curve, and keep all the bunch of curves that you have. Yeah, this is what I told you. Let me say the same thing from an opposite direction. Again, I have a bunch of curves. I just reported the probability of exceedance of the value x0 here. And I just reported them. There are different height because models could have different weights if you want. Then I can build some sort of distribution. For instance, here we have used a beta distribution that is particularly suitable for value bounded from 0 to 1. Therefore, in our view, the aleatory variability is the best guess of the aleatory variability is the center of this distribution. Could be the median, the average, the mode, whatever you want. The spread of this distribution just tell you what is the epistemic uncertainty about this. Epistemic uncertainty that if all models tend to agree, the distribution becomes narrower, and that means that the epistemic uncertainty is much smaller. Now, let us assume that somebody tell me what is the real value, that is the blue arrow. If the blue arrow is there, it means that it's outside my distribution. I found an ontological error. I found some unknown unknowns. So that means that my model is not able to capture all the uncertainty that are really important to describe this data generating process. I'm insisting on the data generating process. Oh yeah, that's okay. Let me go a little bit more into the detail. Here, I have a bunch of curves. The black one, the black one is the mean hazard, and I just cut for this, and then I have 20 exponential curves. For instance, I have 20 values of the probability of exceedance for that specific value of x0, that is 0.29. And I reported here, I can estimate this distribution. This is what we call extended Esper distribution, because it is a distribution that derives from the bunch of curves. This is the way in which we can calculate the distribution. One thing that is important, including or not, makes a lot of difference in testing. In a sense that here we just reported, for instance, one example in which I have a sequence of length of 50 data with 10 exceedances. So 10 ones and 40 zeros. If I calculate this with the mean hazard that say that the probability, average probability should be 0.085, you see that the p-value for this observation is pretty small. If you take into account the fact that instead of the mean hazard, I take into account the distribution that I told you before, the beta distribution, instead one single value that is the mean, of course everything can change. That's, for us, is very important, because if I have a bunch of curves and if I test the mean hazard and I reject my model, it doesn't mean that I'm wrong. It means that the average is wrong, but one of the model, the true model, could be still inside the bunch of curves. For this reason, we have in some way to incorporate into our testing procedure. Just to make an example, here, just to make an example about the experimental concept, let us assume that I have, again, exceedances gathered every year. At a certain point, some people said, well, I discover one parameter, the parameter A. When A is equal to 0, earthquakes are much less likely. when A is equal 1, earthquake becomes more likely, some sort of precursor. What I do now is I change my experimental concept. I won't change anymore, I won't collect anymore the data, a sequence of yearly data, but I will collect the sequence when A is equal 0 and for the years in which A equal 1. In this case, I will have two frequencies that will be different from the first one. Was I wrong? No, I was not wrong. It was right in the former experimental concept. If I change an experimental concept, I change the aleatory variability. Why? Because the aleatory variability is related to the data generating process. It's related to the way in which you decided to assume the exchangeability of the sequence. That for us is very important. Aleatory variability is not anymore related to the real true process of the world that probably we will never know. We say every time that we can define an experimental concept, an exchangeable sequence, we know that a frequency must exist. And this becomes my target. This becomes the frequency that I wanted to estimate. And of course, being a frequency, I can have some sort of uncertainty related to that. And this is the epistemic uncertainty. But every time that you use the mean hazard or an ensemble modeling, you are just simply throwing away all the models that stand around the mean hazard. So that's fine in the sense that the mean hazard or the ensemble modeling is the best that you can do with information that you have. But for validation, for model validation, using the mean hazard causes a problem because you can reject the model even if it is correct, because the true model is inside your bunch of curves, but it's not the mean hazard. Yeah, in this case, I just simply tell you something about what we have done here. We have made two experimental concepts, two new experimental concepts, in which we will have a frequency here, and the frequency of the original experimental concept. All are right, because all are related to one specific different experimental concept. So here, I think that we are getting close to the end. Here I have other experiments, other examples that I can shift, because I think that one important point is just to tell you something about the discussion. And then another important point that I left to the end is that about the subjectivity, because this is an important issue for us. So here, just to recap, aleatory variability is intrinsic to the experimental concept and not to the model. That's important for us. Is something related to the reality. Is the data generating process, not all the process of the world. In this test, the true model and the data are the same, and here I just simply comment the fact that I can have different experimental concepts depending on the information that I have. Another point that is very important, exchangeability judgment can be wrong. That's something also that we have to keep in mind. When you find an ontological error, it's not only related to the model. It might be related to the fact that the exchangeability issue that you have assumed you can test with some sort of non-parametric test if you want, but it could be wrong. And this is also important to take into account. Here I've just reported some very simple example about one site and experimental concept of 0 ones. This can be generalized to many, many more complicated exercise that I reported here, but I don't have time to discuss them. But this is just to tell you what we have done here is just a basic issue, and things can be made a little bit more complicated. For instance, here we have tested, for instance, the number of earthquake generated by a model that has different kind of parameterization all around the world. The basic idea is that using the same procedure, we can test that. The last point that I want to talk is about the conclusion, is about the subjectivity. The conclusion, again, testability, we need to have a hierarchy of uncertainty, aleatory variability, that is the frequency of our experimental concept. Epistemic uncertainty is the fact that we don't know exactly what the true frequency is. We know only that it exists, but we don't know what it is. Ontological error is the unknown if there is the data says something completely different. Exchangeability judgment is exactly this, is some sort of key point to define. And also this makes the difference with some other kind of enterprise, like for instance, I talk about social science or economical science, not always. For instance, the football match, they cannot be easily made exchangeable because the teams are different, so on. So here, you can't make an exchangeability judgment. So in this case, you have to keep using the Bayesian framework because there is no way to use the exchangeability. The fact that we define exchangeability put a limit on the way, on the application of this. That's fine. In natural system works, in most of the cases, not always, but in other kind of interest, like for instance the football match, this kind of system cannot be applied because we can't make any reasonable exchangeability judgment. And again, model prediction of this frequency have epistemic uncertainty that is described by a standard aspect distribution, that is the distribution of all the curves around the mean hazard. And under an appropriate experimental concept is very important. Subjective opinion do not pose any problem. And this is also important because many people in science think that science is objective. There is absolutely no room for subjectivity. And I think that this is completely wrong. This is something that we are trying to convey to the message to the people. I finish with a couple of slides, one from Richard Feynman that wrote this Character of Physical Law, that is a must-read book, that is excellent. And he made a very important claim. It is not unscientific to make a guess. What is most subjective of this? For instance, the Dirac equation has been just simply guessed. And what makes this law great is that it worked. So there is a lot of importance on testing, not on making some subjectivity inside this. And the last one is, the last slide is about the wisdom of crowds. You know, there is a competition, almost 800 farmers make a guess on the weight of oaks just by eyes. Nothing is more subjective than that. But the average of this 800 was less than half pound from the real value of the oaks. So the basic point here is that subjectivity is not important for science. The only thing that makes the difference is the possibility to test a model. Is the possibility to say, okay, take into account all uncertainty, this model has to be rejected or not. This is the only thing that for us makes importance. And thank you very much for your attention. Thank you.